So I'm going live. Tiffany, can you check if the live stream link works?
Yes, let me.
Awesome.
Yeah, I think it's live.
Okay, awesome. So now let's see, Dylan is joining.
Yeah, he's online, so I think he should be coming.
So hi everybody, welcome back to the third day of our workshop. I hope you're all doing well and ready to start the third day.
So Dylan needs a couple minutes. Maybe until he arrives, we could quickly. Everyone's here or not? I think we're missing a couple people, but I thought maybe it would be good to see what the commonalities are between the interests that people wrote down. And now I need to open the sheet too.
Excuse me, did you also spoke about the project yesterday? What are we gonna submit at the end of this workshop?
So yeah, we quickly talked about that, and I can give a recap now. So for the project, we will preferably work in the groups of 2 or 3 students. And this is why we made this participant list, and people can add their interests so that based on these interests, they can group up. And then the project, we described it as having 3 main pillars. One would be the concept, the second would be the mechanism, and the third being the model. So by the concept, we mean this overall idea of what you have regarding shape-changing and adaptive structures. Like, why do you want to make something shape-changing? What is its function? What is its application? Some examples is like imagining something as architectural, adaptive architectural skins, or self-shaping components. It can be wearables, things that you wear on the body and are aimed to respond to the temperature or like sweat. Can be product design. So any kind of ideas that is related to function based on shape change and adaptiveness. The second pillar is the mechanism, and that is what we've worked a lot in these days of the bilayer mechanisms and combination of that with origami and origami inspired structures of how to create something that transforms from flat to a specific shape. And the third is the model. So at the end, what you produce can be a physical model using paper and plastic, or a digital model using the workflow that we gave in the last days, or a combination of both, to have both a digital model and a physical model. The important thing to keep it in mind, especially for the physical, is to think of it as a model of something. The final product might need to be produced with 3D printing or with wood or something, but you make a functional model of it that can be responsive, that can be shape changing, but not necessarily a final material. And it is also based on your own experience, on your own interest, which part of this you want to put more focus on. One person might be more interested in exploring mechanisms, so you don't need to put too much focus, for example, on the conceptual design, but some people might be more interested in developing concepts of adaptive systems and maybe like less focus on modeling it. Or some might even be really interested in developing or building up on a digital workflow to model kinetic structures better. And then, so this is up to you. And then I think with today, what we want to do is to start brainstorming on ideas. For each group, we will create breakout sessions and go like individually to the groups to develop the ideas. And on the last day, which is Thursday, we will have a group presentation. So each of you will just show what you did.
Yeah, okay, thank you.
So
Yeah.
Dylan is still restarting his computer, so I think we need a little bit more, a few more minutes still.
I think another thing we can do right now is to see if any of you made something since yesterday, and if you want to show it. I think Azin, so Azin was here in the previous session, but she said she can't attend the main meeting today. Unfortunately, she had some issues. She will watch live, but she made something interesting that didn't fully work. So Tiffany, maybe we can brainstorm on that later.
Excuse me, I also sent you my two models, and you told that you will speak about it in this session.
Yes, Farishte, you sent me this Origami model, right?
Yeah, I tried it, but it's a little different, and it really didn't work very well. So it's like this.
Yeah, so this is what we saw in a couple of other works yesterday. This was probably our fault that didn't describe it properly. But the thing, like if you look at it closely, you see that the places that these two bilayers are connected.
Yeah.
So this one is bending downwards, this one is bending upwards, and they're connected from the middle.
Yeah.
Then the next two bilayers are not connected.
Mm-hmm.
The next ones are again connected from the middle. And they are like kind of like these two are connected, then the middle one, then these two, then the middle one. So they are kind of, so if you look at this pattern and you look at some some images from the Google, you can understand this.
Yeah.
In the file that we gave you, you also have those red lines. The red lines are cut parts. So if you go the up and down bilayers based on the rectangles in the file with black and then cut only on the red lines, you should be able to get this. But I think in your case, so like you see, there are the lines and then the connection points are in the middle.
Yeah.
Not on the lines.
Mm-hmm. Yeah, it's not, for me, it's a little different. It's I made it like this, and yeah, it's a little different. I think the place that I used the tapes on, that made this problem. Maybe.
Probably. I thought maybe in your case they are connected end to end, or all of them are connected instead of no.
No, it's like
middle to middle.
Yeah, but the place of the tapes, I think. I didn't really make the placement of the tapes as it should make concave and convex shapes. I didn't pay attention to that part very much.
I guess one more thing, if you are taking some principles directly from Kirigami or Origami, you can also make them in paper without any tapes, just to understand the natural curvature. So with the pattern that Yasi showed, like that's a pretty traditional pattern where you can like pull it and understand the natural curvature, and then you can even like draw on the paper to mark, okay, this is going to be a concave, this is going to be a convex curve, and then you understand what side you put the tape on. So I also often do paper models first, and then try to understand, okay, where should I put the tape? It works also for the origami and the curve folding.
Yes, Tiffany, thanks for saying this. This is exactly what I also do. So I first make it without the tape, and then see how it is, and then mark it, and then put the tapes.
Yeah, okay, thank you. And also this other model, I really like it more than the other one. I used 45-degree rotated strips, and yeah, they made this kind of trick. I don't know if it's visible here or not, but yeah, I like it somehow.
Yeah, that's really cool.
Thank you.
Yeah, really nice. Awesome.
I tried the single, I don't know if you can see it, single fold one, but this is dried out, so like the curvature is gone out. But this one retained more of its shape, so I did 2 curves. So I tried the double one, and I was trying another piece. I was trying to get like a square from what you did yesterday, where you put like tape, small strip of paper, and then tape, and then the whole thing is taped at the back. So I added smaller strips of paper in between. So I wanted to try to get it to come back into a square. So this is again drying out really quick. So I just sprayed water, so it has this shape. But then, yeah, I mean, it didn't obviously join because there's nothing to join it at the end. But I was trying to get like a form that would come up into 3D. So, I mean, I haven't gotten anywhere, but that was the idea.
That's cool. That is what the straight crease origami technique, right?
Yeah, exactly. So just the smaller strips with just paper. So I put 3 of them so that I could come back into a square, but then like it at least from going flat, it came into like this shape.
Yeah. That's cool, but I think it also shows that maybe your paper is not expanding too much, because 90 degrees should not be so difficult to get.
I don't know. I don't know if the paper is too thick or like I'm not sure what it is, but yeah, it wasn't as easy. Like the other normal paper was relatively easier to even get this. But it was a slightly more rigid to even get this curve. Like it was actually very beautiful in this, but in this it was a little tricky.
Yeah. The other one looks great.
Yeah, it actually, I don't know why this paper is drying out really soon, but yeah, so it's like that. Yeah.
Yeah, awesome. About the box thing, I think, how wide is your gap, the bilayer gap? Oh, you're muted. Roshni.
Sorry. So these distances were about 3.5 centimeters, and I kept this as 0.5. So 3.5, 0.5, 3.5, 0.5.
Okay, maybe if you increase that 0.5 a little bit to like 0.8 or 1 centimeter, you will have more
bending, right?
Yeah.
Okay, sure.
Because the bending radius is the same, but you have longer, so it can go like.
Okay, sure.
To like.
Yeah. Thank you.
Okay.
Excuse me, can I ask one more question?
Yeah.
About the method of first making the paper wet and then adding tape. I have a little trouble because the paper becomes very fragile. Maybe you can say it doesn't really stick to the form that we want it to be. So this is what I tried to make, and I added just tape in parts of it, but the other parts are also a little not flat. So I don't know if it's okay or I have done it wrong.
So 2 things. One thing is that for this method of first putting paper into the water and then putting the tape, I think in general it works a bit better with thicker paper because it doesn't get like too. And then the second thing is that we showed this yesterday, that if you want to keep a piece of paper flat, a good way is to put tape on both sides of it. So putting tape on both sides is just like block the water. So this becomes like stronger and it keeps flat. It's flat shape. So we kind of use this method for straight crease folding stuff, that Like if I have this and I spray water on it, it starts like falling on there, but then the rest of the pieces remain. So this is also a technique, something you can try.
Thank you.
Does anyone else want to show anything? So Dylan is also here, and whenever we're ready, we can. I think we saw from all the students who wanted to share. But if you still want to show something, just give a shout. Otherwise, Dylan, do you want to introduce yourself? I think you're muted if you're, okay, yeah.
Okay, good. Can you hear now? Yes. Okay, great. And how long do we have?
I think maybe 25 minutes for the talk and then 10 minutes for questions, 10, 15 questions.
Okay, great. So I will try to share the screen. Hold on one sec.
So this is Dylan Wood, who is our third workshop leader for autonomous origami, and he's a group leader of the material programming group at the ICD. He just got his PhD, actually.
Thanks, Tim. I think you need to make me a host actually before I can share the screen.
Okay, I don't know if I can. Okay, great, I can do that. Yes.
Oh, Tiffany, can you make me a co-host? For some reason, I am not a host anymore.
Oh, weird. Okay. Okay. Yeah, okay, now you're the host.
Yeah, cool.
Okay, great. So I can start now? Okay, good. So I think Yazi asked if I can just give a short talk about some of our other work that deals with self-shaping and material programming. That is at a bit of a different scale from her and Tiff's primary research. So I think we usually start with an introduction to our group, but I think you already did this, Tiff. So we will go quickly through that, but maybe we can just briefly touch upon some of my motivation, which comes not just from sort of geometry and material science, but also from architecture. So looking at a couple of really well-known examples, like Louis Kahn's conversation with a brick, in which he asks it what it would like to be, and it responds that it would like to be an arch, which makes quite a lot of sense. But now thinking a bit more, I think as we already see in some of your test pieces, how the bricks or the paper might actually become an arch, which until now was always viewed primarily as an external process on the material that's done by humans or by robots or machines, rather than truly emerging from the material and its capacities internally. And also thinking about this type of problem from the perspective of computational design, which we hope would give us more tools and fresh approaches to do what seems like a very simple task of arranging elements in ways to best accomplish a particular purpose, as Ray and Charles Eames proposed already in the 60s. And I think this takes on a completely new light when we think not just about what types of new materials we have, but how our new tools and computational methods can be applied to existing materials that we actually know fairly well how to work with. So we really see this in my work and also in our group as questioning this idea of the synthesis between material and machine, which is typically dominated by first thinking about the much larger machines and then the material, and is something that has transferred already now over many years into industry for additive processes and also form manipulation. And really trying to think about how we can think about this almost in reverse, to see that the input or the form generation can actually come from the material. So conceptually, it looks a little bit like this, that rather than thinking about the robots doing the shaping, could we actually envision ways in which the material can shape itself? And probably the easiest to understand examples is something like this, which uses curved crease folding as a way to amplify the motion or the change in geometry in a piece, but then can actually be materialized by being built from bio-based materials like wood, and produced in a flat geometry, and then only through drying naturally through the air actually generate the three-dimensional form. So no external machines or anything needs to actually touch the piece in order to reach the final shape. And this idea of material programming is something that we see, of course, in nature. I think maybe you introduced this already, so I can go quite quickly. And the pine cone is maybe one of the best examples because it actually dries out when it falls from the tree and performs this functioning of releasing the seeds incredibly reliably and throughout hundreds of millions of pine cones every year. And this is something that we've studied at ICD for many years now, especially in the context of weather responsive facades and apertures. So something like what you see here, where we can build up parts that respond by curving when they're exposed to different weather conditions. And the programming here happens through the physical composition and the mechanical design of the parts, or the composites, in order to be able to program them to respond in specific types of movement patterns under specific stimuli. And this is something that we tested already in these types of prototypical architecture, like the frac pavilion, where the apertures are designed to open up when it's sunny and then close up when it's raining. And where my work begins is where this work with smaller weather responsive parts reached a sort of pinnacle, but actually in many ways went a bit backwards to try to really think about how wood can be seen as a programmable material for different types of movement mechanisms and different types of scales. So you can see that in a very simple way, wood is a material which is actually programmable in the sense that it has an input, water or moisture, and within the material it can actually compute by doing a sensing, a computation, and then a physical actuation. And the key to describing this as a programmable material is that the wood can actually do this type of movement repeatedly and also predictively. So by decoding or figuring out what's happening in the center part of this chart, we can actually program it in a way that a specific input produces a known output. And the way that wood is able to do this is based on its natural composition. So it doesn't require any chemical modification or engineering to it at the sort of basic material level. And this is an effect that you see already in building construction and product design, but it's usually viewed as a very large problem rather than a usable or tunable function. And this happens based on the microfibril arrangement within the cell walls of almost any wood species, but to different extents. And it's quite simple how it works. When the cellulose fibers are exposed to water, they shrink, they swell, and they also lower their stiffness. And when they're dried out, they shrink and their stiffness increases. And what's important is that these types of movements happen anisotropically and orthographically, which is another key aspect that makes them programmable in larger arrangements. So in timber industry, these types of movements are typically described by like this, like spring, bow, cup, or twist. But they happen kind of unexpectedly, usually when there's a mistake in how the wood is dried, or if how it is cut is not considered very carefully. And the heart of what I work on is how, rather than just letting this type of deformation happen, let's say randomly or unpredictably, how we can use it as a tunable and programmable function to actually initiate predicted changes in shape. So here you can see what this type of material programming process actually looks like. Is that you're starting with a natural material that does still have some known orthographic arrangement of the fibers. And then we're taking apart this material in as few steps as possible in an ideal case, and then rearranging it into a flat sheet that then deforms due to change in moisture into a predictable curved geometry. So if we continue to add on to our chart, we can add this arrangement and orientation, as well as an additional set of mechanisms, which combined with the actuation on the material level can produce not just volume change, but also a change in curvature. In reality, it doesn't look probably that cool when you think of computational design or digital processes. So you still have to start with the large chunk of wood. In this case, it's actually really cheap, one of the cheapest pieces of wood that you can buy. So not as cheap as paper, I guess, but actually maybe per weight or volume, it's cheaper than paper. And then basically cutting this up in a very sophisticated and informed way, and then assembling it into the flat sheet. And then every triangle within the flat sheet is arranged with a specific orientation of the fibers, and also detailing to connect it to its adjacent elements. And once these are assembled almost like a puzzle, this seemingly innate flat sheet can deform into a three-dimensional geometry. And this can happen at the scale of 1 to 2 meters. So much larger than a lot of the things that Tiff and Yazi might have shown. But also it's important to note that here we also reach the sort of lowest level almost of resolution in which we can tune the behavior. So that's how it nicely compares to the 3D or 4D printing work. So this is what it looks like as it gets up over a couple of days in the lab. It's a very natural movement, almost like an animal or a sloth. So then now, based on these concepts, I want to share two of our slightly larger projects that use this idea of material programming for construction and assembly. So the first is the Urbach Tower, which you might be familiar with, which was constructed in 2019 as part of a federal or state level garden show outside of Stuttgart, as a building that will last for 15 years outside. And this was done in collaboration with the ITKE at the University of Stuttgart, who we work very closely with on many of our projects, as well as a very tight scientific collaboration with the Laboratory for Cellulose Materials and Wood Material Science at ETH Zurich. And again, very tight collaboration with Blumer Lehmann in Gosau, Switzerland, which is a well-known timber manufacturing company. And the basis of this was to really look at how CLT, or cross-laminated timber, has sort of like aided in the resurgence of timber in larger scale construction, especially multi-scale construction, but at the same time, the sort of flattening out and let's say uniform construction of CLT means that it often results in these types of almost cookie cutter or box-like structures, which work well for building really quickly and building, let's say, cheaply, but actually don't necessarily use the structure of the material or the geometry in the most efficient or effective way. And if we look back a bit to even the most basic, let's say, structural engineering education, as an architect, I think most of us would know that if we take the pieces of paper that you have even today, and you try to have them cover a span, like on the left, they can't really do it so well. But as soon as you induce some curvature or some depth, you're able to actually span the same distance and carry a much higher load, even with a really thin piece of paper, or in the case of our project here, with really thin sheets of wood or CLT. And so we can wonder why we don't use these types of geometry already to build structures like towers or roofs in a slightly more effective way. And of course, with timber, it is possible to build curved geometries. And I think a lot of these types of projects are really well known, and the digital tools have made them easier to construct, but they still require an immense amount of planning, as well as physical force and material waste in order to actually manufacture them well. So the basis of any type of glue laminated curved structure, like what I showed in the previous slide, is that you need some type of existing shape to push against the wood in order to change it from this rather linear shape and elastically form bend it into a curved shape, and then hold it while it's being glued. And the problem with this is not that it's necessarily impossible, but it makes it significantly more difficult and also more expensive to produce curved geometries. So often it's cheaper to just use a straight sheet with twice as much material than it is to make a curved piece. Or it's even sort of less desirable, at least from our perspective, in that it's cheaper to just build a square piece and then remove it from it until you reach the specific curved geometry that you want. And of course, this is not ideal, let's say, sustainable from a sort of ecological perspective, but it also is not ideal from a structural perspective, because it means that you end up with many fibers that are oriented in completely the wrong directions for taking the load. So if you consider the work that we showed before, the key for us in order to generate larger changes in shape in pieces that are sized to make sense for actual building construction or building components, we had to be able to predict the movement that's caused in the wood in larger pieces. So we work with finite element method, as well as more analytical methods in order to be able to build models to predict this type of movement. So I won't go into so much detail about this, but you can read about it in our publications. But this involves building not just an FE model, but also incorporating models that take into account many of the more complicated material characteristics of a material like wood. And when we're able to do that, it means that we can more accurately actually predict the movement, plan it, and also adjust it, adjust the sort of key parameters in order to produce a specific curvature that we're looking for. So once we're able to do that, it means that we can actually produce these 2-layer sheets, which are in the scale of multiple meters, in a flat configuration with design thicknesses and a couple of other parameters. And then when these pieces are dried, they will form curved sheets. And then we can combine these curved sheets again in order to lock the movement in place, in order to get a curved or highly curved form stable CLT component with which we can build. And at the same time, from more of the architecture perspective, we looked, in this case for this project, at how we might be able to use these high curvature wood sheets in a way that is both structurally efficient, like what you see on the top, for a vertical oriented structure, as well as how we can induce certain architectural features using a minimal approach to let's say, geometric manipulation or geometric parameters. So on the top, you can see how we're able to create this sort of curved or corrugated surface active structure, which works specifically well with these high curvature thin sheets. And on the bottom, by just slightly twisting this or slightly shifting the angle of each of the single curved geometries and then intersecting them, we're able to create an overall double curved geometry that works even better in terms of surface action. So this is a bit low res, but this is what the geometric approach looks like. If you are looking on the internet as to how this is made, I would caution that many of the YouTube videos out there actually don't model it correctly. So if you're interested in this, we could also, I would also be happy to explain. But it's very simple. From a single curved cylinder, by intersecting 12 of these around and then taking the surfaces at the intersection, we're able to generate an overall double curve shape from single curved components. And then, of course, we also have to develop the constructional systems in order to be able to link up these components. So here we use crossing screws, which are inserted with pre-drilled pilot holes at specific angles and spacing in order to connect the different components along a still ruled but twisting surface. And this is where our engineering partners at ITK come in, because of course the self-shaping means that we need to use a relatively unique buildup within the material, which then has to be designed in a way that it can be compatible with both the overall bending behavior and the material utilization, what you see on the left, as well as compatible with the connection system of crossing screws, which I showed in the previous slide. Then maybe the most interesting slide from a design perspective is that all of this computational design work then comes back to this guy at the beginning of the production process, because in selecting the boards based on the parameters that we have in the very beginning of the manufacturing, he's able to actually encode the physical information into the parts so that later they will deform into a specific shape. So all of the digital stuff in the end comes down to informing this operator which types of material to select for which pieces. And this is done at the time partially digitally, where he's able to read the specific parameters like the moisture content and the grain orientation on the screens. And then with a flip of a button, he can put them into specifically sorted categories in their sorting system. And then these will be pulled out or dumped out automatically when one plate is ready and can be constructed. Of course, there's quite a lot of variation at this level because we work with a natural material. But what's important to say is that, of course, we record all of the material parameters throughout the process. And despite relatively high variation in all of the boards, of the many hundreds of boards that we use throughout the components that were built from the tower, using our computational design methods, we're actually able to still get an arrangement that produces a relatively fair prediction of the curvature. So after the boards are selected, they're manufactured into these 2-layer plates using a standard press. And then they're put into these racks, like what you see here, and then into the kiln where they will be dried alongside all of the other boards that are used for other applications in timber construction. And inside the kiln, this is where the sort of magic really happens, because over a couple of days during that drying, then each plate shapes into this curved geometry with a 2.4 meter radius. And this all happens sort of automatically. So all the boards shape at the same time, which is a big advantage compared to using a robot to bend things or other types of physical forming. And it also happens in a workshop which actually doesn't do form bending by any other means. So there's a real advantage in that this type of forming process doesn't require any additional equipment or tools or robots. It just requires a very specific and educated use and orientation of the material at a slightly earlier stage in the manufacturing process than it would usually be considered. After the plates are sort of pre-curved, then they're taken to another hall down the road. And here it's a bit messier, so we use a drawing to explain how this works, but each of the multiple meter long plates are then basically nested and combined in 2 layers in order to form blanks from which the final curved CLT components can be nested and cut out of. So this is what the components look like when they're finished after they've been cut from the larger blanks. So these in the end are almost 15 meters long, and they're made up of 2 combined layers of these self-shaped plates that we saw already in the drawing kiln. Another advantage of this type of approach is that there is no springback from the forming process, and there's very little material waste, which means that the only type of like finish work that's needed is really like a careful trimming of the edge, and almost like a dentist, the robot coming in very precisely with a 3 millimeter drill bit to add the connection detailing and the pilot holes for the crossing screws. So if you imagine that the part is basically already shaped, all the robot really needs to do is to come in and precisely add a couple of holes and finish and clean the edges around the connections precisely. Then after these are manufactured, the components are combined in groups of 3, and a weatherproofing membrane is added along with a larchwood glue laminated facade to protect the structure from water. And then these are transported to the site in groups of 3 or 6. And then on the site, it takes only a couple of hours for the workers to assemble them into the tower structure by basically inserting screws into the pre-drilled holes after each group is lifted up into place. And this results, of course, in a structure that is almost completely wood in its load-bearing capacity, other than this very, very thin 10 millimeter steel ring at the top, which prevents ovalization and also provides an interface to connect to the polycarbonate roof, which protects the inside sheltered area. And this results in a sort of very quick assembly on site of a structure with a very unique geometry. So on the outside of the structure, what you see in a couple of the images is that it has very sharp lines that sort of catch the light and distinguish it as a landmark. Whereas on the inside, it has a completely different type of feel or texture. And the entire wood structure is only 90 millimeters thick, but it manages to cantilever 15 meters into the air, which is a rather impressive slenderness ratio if you were to calculate this. And what I find somehow the most stunning is really the architectural impression or spatial experience on the interior of the structure, where this wood, which serves not just as the load-bearing structure, but also as the walls and the finish, also takes on a completely different type of spatial texturing, which is almost like a pillow or a fabric, even though it is actually carrying the entire load of the building. So it's almost like a pillow type experience, despite the fact that it's carrying lots of load. And on the interior, this also allows the structure to be lit from the top, and the walls are sort of washed with light, and on the inside it becomes a sort of reclusive space or a space of internal reflection, which frames very differently the natural landscape that surrounds it. We don't have to do anything to the surfaces. These are sort of, they function as wood, as a finish, as structure, and they're also very friendly, which I think adds to the simplicity of how the construction is actually materialized. So there are fewer steps, fewer types of coatings, fewer materials involved in the end. And it's also important, just to wrap up about this, that somehow this allows the structure to sit very precisely, but also very nicely within the actual natural landscape surrounding the village. But of course, our sort of research projects don't really end there, because we also have to monitor how the building is changing over time, specifically in relation to the moisture content. Which is actually used to generate the form. So some of the biggest fears are that that a change in moisture content from the weather would then cause the structure to reshape back into flat surfaces. So what we've done is installed sensors within the buildup of the wood, which are then monitored with a data logger and reported every week back to us. And what we see is that even though there's a relatively large natural change in relative humidity throughout even a day, which is what's shown on the top in the yellow lines, which are a bit difficult to see. This also results in a relatively large change in moisture content in the wood. But because the plates are sort of locked together, it doesn't result in much of an overall change in shape even after a year since the construction. So what we see in one of these recent scans is that there are only really minor deformations at the top of the structure in the range of 10 to 20 millimeters, which for such a tall structure is relatively small. It's also interesting to see the sort of social reaction to these types of structures, which are, of course, not always what we would expect, but we have to somehow also admit that our buildings, although they are research, also somehow live within the culture and society. So I think this is something that we tend to somehow omit, always by just showing the fancy images, but this becomes more and more important, I think. That we learn not just what's there on the first day that the building opens, but also what happens a couple of years later. So, of course, there are people that love these types of buildings and people that criticize them. But I think we also start to learn how they begin to live within the nature and also the fabric of these types of communities. So on the outside, just as an example, the building was designed to actually sort of changed its color over a couple of years. So it's changed from this sort of much brighter, but sort of yellow color to a light white. Okay, so now, Yasi, if there's time, then I will just quickly explain another project. Is that okay?
Hygroshape is the wood 3D printing projects from the students. Is it?
No, this is the furniture project.
Oh, okay. Yeah, of course. I mean, but make sure that you have time for the Q&As as well. If you need to leave at 3.
Okay, then I will just go
quickly.
very quickly. Okay. So then what we showed before is really about a sort of implementation and adaptation for timber construction. But in parallel, we've also worked on some smaller projects which deal with furniture. And with the reduction in scale, we're able to look at, let's say, higher implementation in terms of functionality that moves just not only from a sort of prefabrication process, but also to ideas of self-shaping in situ or self-assembling outside of the factory or controlled manufacturing situations. So one of the best examples is really simple. It's for furniture. And furniture, even really nicely made furniture like the Eames chairs, are still actually produced like with a sort of contraption or a machine, which you see on the right-hand side, in which the materials are physically pressed into a three-dimensional shape and then sent to you in a giant box with a lot of air in it, even today. So these types of processes haven't changed so much over the course of 50 or 60 years. It's just that the boxes have probably gotten bigger and the machines have gotten a bit stronger. The other option, of course, which you probably know, is something like flat pack assembly of a chair or a table from IKEA, where the furniture manufacturer nicely compacts all of these nicely made parts into a small box, and then you pick them up and bring them to your house. And then you're left with the relatively straightforward, but maybe complex for some instructions of how to actually implement them, and a collection of strange tools, which we all probably have many of across the world, in order to be able to get again to this more three-dimensional assembled shape. So the basis of this study was to look at how we might be able to use self-shaping in wood in order to replace actually both of those types of issues in the manufacturing of three-dimensional furniture components. So the idea is quite simple, that we produce the parts flat in the factory, but with specific combinations and arrangement of the wood, so that once it arrives in your house and you open up the package, it will slowly shape into its final geometry. So we can quickly watch this to explain. So maybe the most important part, despite our fancy video, is what actually happens when you open the package. So here you can see a full-scale prototype. When we're releasing it into the wild or into the environment, that's able to sort of first shape up its back, and then very slowly the bottom actually push the chair up into its fully assembled configuration, which will stay this way unless, of course, it's thrown into a swimming pool or something, exposed to relatively dramatic change in conditions. And again, to go back to the aims quickly, one goal was to increase the volume, so that we achieve here with almost a 30 times change in volume compared to the transport volume, and also to be able to do this without the need for any tools or special instructions or knowledge in the home, which I think you can see in the videos happens without any people involved or any tools. And again, it relies simply on a relatively clever arrangement and organization of the material in the flat state that then generates this three-dimensional geometries. It also means that these types of relatively elegant, lightweight structures start to emerge that are able or capable of carrying higher loads with very little material, which wouldn't necessarily be conceived or manufacturable using normal types of form bending manufacturing. So I think that's it, Yazi. And we have a few minutes to answer some questions, or I could also join a bit later if you want.
Amazing. Thank you very much, Dylan, for this presentation. I never get tired of watching it, even though I've watched it before. So let's get to your questions. Go ahead, unmute yourselves and ask Dylan.
Hello, I want to thank you for your presentation. It was really interesting, and I also attended your PhD presentation, and I'm really interested in your work. I think the way you use very natural ways to form the structures is really interesting without using robots or high manufacturing techniques. I have two questions. One of these is you used in your tower, you showed that you shaped different parts and then you assembled it to make each of the twisted particles, right? And I want to know how you calculate the final form, because maybe each of these particles respond differently to the change in the moisture, and how can we shape the whole twisted part based on these different particles that we combine them together?
Dylan, you're muted. Oh, Dylan. Hello.
Okay, sorry, I can answer I guess more specifically about the tower. I mean, because it is a natural material, there is always some variation, of course, within many of the boards. But what we actually, the types of parameters that we control are actually shown here. So it's maybe a little bit small, but the main things are, of course, the moisture content that the wood starts with in the active layer. So in this case of the tower, like the wood was like almost freshly harvested from the trees, so it has a really high moisture because it's going from being basically living function to building material. It's like in a transition. And so the key is that we somehow select out the boards that day that have moisture content within a specific range, and then these are kept in a relatively controlled environment until the bilayers are produced. So that's probably the biggest parameter, which is also the most difficult one to control, because like I showed in the monitoring, there's always moisture going in and out of the wood, right? Also with your paper. So I mean, I think even in the interior environment, your paper probably changes 10-20% volume in the course of a day, even if you just like breathe on it, I bet. But so that's one parameter, and then the other thing to consider is the thickness, and this we can control pretty precisely, and also the grain angle, which is here we describe it as the RT plane, and this also we can control moderately well by choosing the pieces from like specific areas of the tree for the plates that we want to build. Okay, but Yazi, I think unfortunately I need to be very on time to this other thing, but I'm happy to join a bit later if you want. And also tomorrow might be a bit difficult, but we can discuss. Is there a time today that would be good? Like in 1 hour, is that too late or?
No, that is good. We will be here until 5. So if you come in 1 hour and you can ask the rest of the questions, that would be
Okay.
great. Awesome.
Okay, great.
Thanks,
a lot,
Dylan.
and good luck. I mean, I hope I can join for the end of the workshop as well.
Yeah.
And I'm very much looking forward to it. So thanks.
Yeah, thank you. Then see you later, Dylan. Okay. Okay, so we couldn't get to the rest of your questions now, but we'll get to them in 1 hour, okay? All right, so I think now the next thing we want to do is that we want to get to your groups. First, I don't think, I mean, I'm not sure if you have groups right now. It doesn't seem like it. So maybe get to the sheet, look at your interests, make groups, and then based on the ideas, we can start working on them. So we should do that today and tomorrow, and then on Thursday, it's the presentation. So does that sound good?
Does anyone already have like an idea of who they want to work with? And also, so you can already maybe start forming, but also if you don't know, you can also talk to us and we can also try to help pair based on some of the interests. So we want to promote like a natural kind of grouping. So just, feel free to try to decide amongst yourselves. But if you need a little bit of help to find a group, just let us know.
Should we be like thinking of pairing or teaming up in terms of like similar types of interests, in terms of like, let's say, should the people that want to make a digital product for this group project work together, or instead have, someone that wants to do a physical model and a digital model to pair together, so that, one person can handle like one sphere of things and the other can handle, the opposite?
So, it's so crazy. There's like a storm. There's been a storm in Stuttgart, and like it's starting again. Okay, so anyway, I think it's entirely up to you. I think if you have common interests in terms of like either like the application or I don't know, the mechanisms that you want to explore, I think that could be the main driver. But I think it's not necessarily that you have complementary physical or digital. Like the group can also be a much more physical exploration that you do sort of together. But I think what's important is that you have like sort of similar interests in terms of what you want to explore. So if you want the other person to also do a complementary, because I remember you were saying that you're much into the physical aspects. So if you feel like that's missing, like the digital part is missing for you, that you would like to also include, then that would be a direction that you could, or that could be like a criteria for you. But I think it should be pretty open for everyone.
Okay, yeah, that makes sense. I'm just wondering if, we have some time to, and this is just an idea for us to kind of go, I know we have like our interests listed on this spreadsheet, but to kind of go around and maybe share like what type of like concept we wanted to potentially work on, and then maybe we can see if anybody is interested in similar things and be able to team up that way.
Yeah, Azim, this was actually what exactly I had in mind, that we would go on a break and we come back, and then each of you take just a few minutes to say what you want to do. The initial project idea you have, whatever, and then you can match like, oh, these two sound good. So yeah, we will start with that. But now we have Dylan back, so he can stay for I think half an hour, which should be more than enough for our Q&A. So we can get to that now while the topic is fresh. Okay? So go ahead and ask some of your questions from Dylan Wood.
If there are no questions, it's also okay, Azzy. Oh wait, there are some.
Hi, Dylan. I had a question regarding the chair that you showed us at the end. Do you hear me? Yeah. Okay. So I'm not sure if I got it right, but you said that the chair would retain its form unless exposed to water, right? Is that what you said?
Yeah. So we use a couple of tricks in how we prepare the wood. In that case, which I think we can't really say in so much detail, but like basically that it will perform a very large change in shape, like what you see in the video, and then of course, like in your house, it will like the moisture, the humidity is always changing a little bit, but this would cause like small movements in your chair.
Okay.
But it would not cause it to like go back down to being flat. And I think maybe, I guess Tiff and Yazi are not in the institute, but like this morning our institute flooded apparently because a window broke. But I have not heard any reports that the chair is flat. So so I think this is a good proof that that we don't have an issue with it going back down to being flat. So it's really intended as like a one-time you get it, you open it up, and then on Friday it's shaped, and then it moves around a little bit, which actually is quite interesting because we always thought that this moving around is a bit problematic, because like if you order a chair, or like I don't know, you order a chair and the shape is like one thing in the picture, and then it's like slightly different when it shapes and arrives, then you probably like the first reaction is like, oh, it's like not it's like messed up, right? Or like they sold me a bad one. But actually, when we started to look into this idea that especially with furniture, that like the ergonomics change over time, is actually a really desirable function in a lot of fields. So like, I guess if you have, I have a really terrible chair here, but it doesn't move. But I guess if you have an office chair, a lot of like more expensive office chairs, when you can actually like adjust the seat, right? Or you can adjust like the support in the lower back. And so a little bit of research, we found that actually like if the lower back support was to move, I don't know, a little bit each day in a kind of like relatively unpredictable way, this is actually some sort of really interesting research for ergonomics. So yeah, I guess it's also somehow how you always look at it, because we spent 2 years as someone telling us that this was like a terrible feature, again, that it might not look like the picture. And then in one conversation, like someone else thinks it's like basically the best thing ever, that they've been trying to, I don't know, invent a way for something to do that passively for like 10 years. So I think it somehow is always a bit looking at the perspective.
Sure. So the actuation in the whole process is just natural, right? Like they just open the packaging, and once exposed to the natural environment, it just goes to its form.
Yeah, it starts going to its form, but it's not fast. So because it's slightly thicker, it happens like slowly over 2 or 3 days, depending on what the environment is outside. But that's also something quite interesting, because it really gives you a slightly different perception of time. So I think this is also maybe what you see in your samples, that I mean, I don't know what you were expecting when we did when you signed up for the workshop, but everyone always expects that the things work like almost like instantly. Like now it's flat and now it's shaped. But actually, I think like even if you just take the time to try and like watch them, I mean, it's a very, very interesting thing when something moves, but you can't perceive the motion. And I think, again, that like some people think that that's negative. Like if you're making an exhibition for a museum, like they say, oh, like you can't see it move, so we don't want it. But actually, this idea that something moves, but you don't perceive it, can also be really valuable, because like it also doesn't distract you, for example, or it can't like injure you by popping out, right? Or it can't, it doesn't make any noise, right? And we think, if we think about that, those types of characteristics or traits of the movement, then we can see that it's really not that we're trying to replace the movement of a robot, but actually that what you're working with is something that really has a completely different set of characteristics. And I think that's also what we find so interesting about it. I think one day we want to do a sort of survey of what people think of the movie, or we want to do like a 60-minute lecture where there are no slides, and all you do is watch the movement of some of Yazi's parts real time. I think that would be that if we talk about sort of experience level, that would be something that would be somehow like mind blowing, I think, in a lot of ways. To really sit and like be able to watch to be able to sort of experience the movement.
I have a last question regarding the same product. In principle, I would, go, based on the experiments we did in the past 2 days, this would be closest to the reverse programming, right? Like the behavior.
Yeah, meaning that we put the paper in the water first, let it there in for 5 minutes, take it out, and then put the tape.
Yeah. Thank you.
I think so, right, Dylan? I mean, I also had a similar.
I mean, I think in what we show, it's always like this, because this is the easiest to achieve. But we've also looked at some, I mean, there are some practical problems as well. Like, for example, that the wood is heavier when it has water in it. And so if you're shipping something, then it's not so good to have it be heavier as well as to be wet, right? Because generally you want to keep everything dry when you ship it, right? Wet things in a manufacturing hall that's not making food are usually considered to be pretty negative. But we've also looked at doing extreme versions of the reverse. So like, could we like dry, like, I don't know, there are some really extreme ways to dry wood, like beyond like what you get through just exposing it to, like, I don't know, the air. And we've also recently looked at some approaches that might take that method. So like drying it out like almost completely and then sealing it. So then it's like lightweight, not wet. And then when you put it in your house, like even if the humidity is relatively low, it still is so much different from whatever we glued it at that it will like start to shoot up. So I think again, it's sort of like picking which things work in relation to where you wanted to, what you wanted to do.
Thank
But
you.
how's it going with the paper yet?
I think it's going well. Yeah, we have seen some really nice stuff. A lot of care foldings, more successful than the ones I made. And yeah, I think it's going pretty well.
Cool.
Excuse me, I have also another question. Can I ask?
Yes, sure.
Yeah, thank you. I want to ask about the structural performance of making these forms using moisture. So is it have a test done on how is the difference between the structural performance of this kind of self-forming and other kinds, like using CNC milling machines or whatever?
Yeah, so for the tower, I guess maybe you have to explain that for the furniture, it's a bit different from the tower, because in the tower, the parts are like a whole bunch of parts, like your pieces of paper are shaped. And then we glue, once they're curved, we glue them all together. So then they get like stuck. Like you could also do that with your paper, actually. Like you could shape it and then glue it, and the glue might cause it to actuate again, but I don't know. You could imagine the same type of thing, except it's very easy to bend the paper by hand, which with wood it's not easy to bend with your hands. So so those are two different things. So the one in the furniture is of course a bit weaker, right, than a form bent piece that's glued out of many layers. But the in the tower, it's basically structurally equivalent, at least by test, to a form bent piece. And we sort of benchmarked this to bending to parts that were made by form bending, like with a jig or like a mold. And it has the same, if not better, structural performance in the end, depending, of course, how you test it, because we have a geometric, sort of like fiber orientation or like layup configuration that's kind of unique for CLT, because we have something like 60 or 70% in the direction perpendicular to the curvature, and only 30 or 33% in the direction parallel to the curvature, which is it's not normal to have such a imbalanced buildup. But basically, in order to get the building permit, we had to test it in like a normal 3-point bending test and a shear block test for the gluing to prove that it was at least as strong as the other pieces.
Okay, thank you.
But it was tested in Switzerland, not in Germany. That's maybe also important, because Germany has much more difficult gluing standards, as we know. Well, yes, he doesn't know, but she'll soon learn, I guess. Okay, any other questions?
Hello, I have a small question regarding the geometric stuff in the wood. So basically, for the paper folding and also this origami stuff, they stick to the developable surface in the geometry side. So how about the wood? Does it also stick to a developable surface, or it kind of changes in the doubly curved surface?
So I think that's a bit the art of the art of what we've done geometrically is that the actual surface components are still developable. But the way that we've arranged them, the overall shape is a synclastic sort of shell. So it's curved like this and like that in the tower. But we've also looked at producing double curved geometries, which was less successful. It is successful, but it's not as predictable. So this is why we sort of stuck, at least in upscaling to that scale, to single curved or developable surfaces. I think Tiff has maybe she showed also some 3D printing pieces where she's able to produce more synclastic geometries by basically tuning the stiffness or the stretching in certain areas of the 3D print, which is definitely an advantage of the 3D printing. And we've also looked at like grid on the sort of extreme end, which I think we can't really then call it a composite sheet or a composite material. We've looked at like grid shells, for example, that can deform from flat into a synclastic or anticlastic like overall shapes, but are really in a different range of geometric mechanisms where the deformation is a combination of the material curving and a deformation or a rotation in the grid axes or the pin connections within the grid. So the short answer that we can get double curvature, but not using really big solid sheets yet.
Okay, yes, thank you very much.
Okay, great.
Okay, thanks a lot, Yazzie. That's it.
Thanks for coming back, Dylan. Yeah, I think
I
that's it
will
for now.
stay for a few minutes and then yeah, let's discuss if I can join on the last day or something if you want. Okay.
Yeah, would be great. Okay.
Bye.
Bye. So I would suggest that we go on a 5 to 10 minutes break, 10 minutes break. And then we come back with the initial project idea pitch. Individually, just each of you saying what you want to do, and then we can team up, okay? Awesome. Then let's meet each other in 10 minutes. Bye-bye.
The storm is crazy. I don't know if you see the flashing, like.
Yeah, what is happening? I didn't understand. There's a window that broke?
No, there's a really bad storm. Last night, it was like so much thunder. Now there's like hail that's 1 centimeter large. Like yeah. I don't know if in Constance, see if it's also like that there, but
we had that last night. And it really felt like the house is coming down. It was so loud and all the windows were shaking. Everything was shaking. It was horrible.
There's like trash all over the outside streets. There's a construction site outside and all the like dividers have fallen over. There's like random bed sheets on all the cars that flew from random places. And I wanted to go to ICD to check, but I can't go out right now.
It's horrible.
I guess I don't understand what happened at ICD. Maybe like if you leave the window open, it can like slam.
Yeah.
I guess maybe.
So if they didn't fix that window,
and then it's like, I don't know.
Yeah. So that window is completely gone. The whole thing shattered. And if they didn't replace it by now, then it's gonna flood again. There's so much rain.
This is crazy. How,
The hail is huge.
but how can you break? I mean, it takes like a pretty big amount of force to break a window like that.
Yeah. I mean, if the construction site is like toppled over outside here, then it can for sure break the window.
I hope the roof has not blown off the tower.
Yeah, so I wanted to go to ICD to check the stuff on the roof, but no, I was worried after hearing about the damage. I wanted to go check, but I can't. I have to wait till this dies down before I can go.
That's crazy. Yeah, I guess you should. Yeah, you should check that.
Yeah, I hope it's fine.
Or it could be like in the other side of Stuttgart by now.
I was worried that there would be like a fire, like when I first left, like over the break, over
Christmas. Like a sort of absurd storm, like right after in the summer after the tower was opened, and we thought, of course, this is like maybe the maximum wind load, but now I'm getting a bit worried.
No, this is the most intense storm I've seen here. So I wonder if I mean, a lot of the trees got uprooted and like fell over and stuff. So there is a tree next to the tower, right? Like that could be falling over onto the tower.
Anyway.
Yeah, I don't know how you check.
How is the workshop going though?
I think it's good. I mean, the students are making some really nice, like they're making nice models. They're getting the hang of it.
That's cool.
Yeah. I think they're understanding the programming part quite well.
Does it work though with the, I mean, does it actually work?
With the paper?
Yeah.
Yeah.
Okay, cool.
Like we have like this one, and then, I mean, it's a simple one, but so far, we haven't done anything too complicated yet, but.
Okay. That's pretty cool. Okay, there's a tower. There's a picture from the tower from yesterday afternoon. When did the storm start?
It started like at 6, I think, or 7. Yeah.
Oh my god.
So probably 7. Let me see.
If the roof goes off the tower, I'm gonna.
Yeah, I'm a bit worried about your tower, but I think more so like there are a lot of trees that got uprooted.
Oh,
and like,
yes, he says that we're on live stream.
Oh, okay, I guess we should take this offline.
All right, thanks, Yazzie.
Hello. So I am back. If you want to chat, just بچه ها اگر سوالی وجود به کار دیلان یا هر چیز دارین میتونید فارسی هم بپرسید، من سعی میکنم جواب بدم یا دیلان رو دوباره بپرسید.
من یه سوالی دارم که البته پرسیدم ولی دقیق راستش متوجه نشدم. اینکه همین حالا تیکه های این برجی که طراحی کرده بود دیوان، این اومده بود از یه سری تیکه های جدا از هم اینها رو درست کرده بود. بعد برای من سوالش اینه که این فرم نهایی تویست شده رو چجوری میتونیم پیش بینی بکنیم بر اساس یه سری قطعه‌ای که جدا از هم دارن فرم میگیرن؟ یعنی ما چجوری میتونیم مثلا همین بایلایر که فایلی که خودت دادی به ما، این اینطوریه که خب دقیق نمیشه گفت دقیقا همین فرم قراره بشه، درسته؟ پس چجوری مثلا میشه کاملا مطمئن شد که این قطعات کنار هم قرار بگیرن؟ این میزان مثلا روتیشن رو داره که بر اساس اون قطعات کناریش چجوری قرار میگیره که کاملا چون اینترلاک شده بود و
آره ببین واسه اون پروژه تاور اینا با گروه وود ساینس توی ETH کار کردن. اونا تخصصشون روی این سازهای چوبیه. اولا که مدل سیمولیشن خیلی خوبی داشتن که با فاینت المنت بود، نه حالا مثل چیزای ساده‌ای که ما داریم. و دوما این که اینو توی کارخونه‌ای ساختن که کنترل خیلی خوبی روی چوبا داشتن. یعنی حالا یه سری عکس نشون داد ولی چوبایی که همه اصلا از درخت مشابه گرفته شده که با هم دیگه رشد کردن و تیکه‌های چوب هر کدوم اندازه‌گیری شد که مویسچر کانتنتشون چیه. یعنی یه سیمولیشن خیلی خوب و یه پروداکشنی که بالاخره بتونه از توی متریال طبیعی اونایی که بیشتر از همه شبیه به هم رو پیدا کنن ازش استفاده کنن.
درسته. پس سیمولیشن که اونا داشتن یه چیزی کاملا بر اساس FEM بوده و یه چیز کاملا دقیق، یعنی صرفا یک مدل
خیلی دقیق تر از چیزی که ما داریم. باز نمیشه گفت که 100% دقیق چون که متریال طبیعیه و هیچ وقت نمیتونه که پرفکت سیمولیت بشه، ولی بهترش.
مرسی.
So just that there was a question, the same question about Dylan's project, and I just tried to give Dylan's answer in my own words. Okay, so it seems like everybody is here. So let's do this. Let's go one by one and have an initial project idea pitch now individually, and then we can team up, okay? So who wants to go first? Should we go by the list of participants or does anybody want to volunteer?
I can go first.
Okay.
Okay. I want to use these origami forms for shaping the canopy, and the importance for me is how they are form found, and also the structural stability of them is really important for me. So I made something like this. It's similar to the form that I previously made. But I understood that if I cut the places from different two parts, it helps them to something like overlapping in the middle and make a structure. So this is what I thought about.
Cool, interesting. So in the middle, the pieces that come together and twist into each other, you want to like use that as a structure.
Yeah. Besides, I'm working on active bending structures, and I'm trying to make a structure based on this new type of material-based performance. So,
Cool.
thank you.
Cool. Awesome. So who wants to go next?
I can go. Let me turn on my camera on. Okay, yes. I'm wondering if we can mix the folding line with your system. I mean, the wedding system. I try to split the complex origami form to some rectangular form with the fold line in between. I don't know if you can see the fold line. This is the fold line. I fold it from the diagonal. And then I tape it. And then I spray the water and it shapes like this one. But I have the fold line in between.
Okay, so there's a fold and then the flaps also bend.
Yeah. And I try to expand the fold line into a big triangular. I mean, one fold, and I have 3 folds here, one in between, in the middle, and 2 in some sides. It's make me to grip like this. And then we spray the water, it can shape like this. I try to figure out if I can make a big tessellation with combination of these models. I try to things like modularity, if I can set a pattern of modular rectangular or not. That's the concept.
Okay, interesting. So you think that you can have like a surface, a big surface that is composed of these modules.
Yeah, that fold line helped me to connect each pattern together to shape a tessellation.
Cool. Tiffany, feel free to say something, but I think we don't put too much comments right now. Let's just hear the ideas.
Yeah, I'm just noting down some of the concepts so that we can try to see if there are any overlaps.
Awesome. So Thursday and Fatami went. So now next.
Just I have one question. When we let the curved origami to be dry, it's not get the simple shape. Yes, it's not back to the simple flat shape. Am I right?
It almost goes back. I don't know.
Because, for example, in this form, I let it dry and nothing's happened after the process.
So I've also noticed that like this one that I made yesterday, because I kept it sort of in that shape as it dried, it then stayed. So I think if you like hold it like that for a while, then it also, but if you just leave it, I think it should
No,
go down.
I just leave it.
Okay.
I just want to check it if I'm right or wrong.
I think it also might depend on the type of the paper.
The thickness, you mean?
The thickness and also the type, the like internal structure of the paper might also affect that. Because I have some samples that went pretty much to flat, and I think one sample that didn't, which was from another paper. So it might be that.
Yeah, I mean that's. I don't want to take away from like the presentations of like the interests and stuff, but I think it also it was my first time experiencing that with the curve folds, but with the ones that are just a simple strip, they do go flat. So I wonder if the folds somehow stay once it shapes, then it kind of keeps the crease, and so I guess if you just leave it without like pressing it back down, then it'll try to keep the shape perhaps.
I will try later. Thank you.
Yeah. Try wetting it and then just like flattening it out and then see if it stays.
Thank you.
So who wants to go next? And guys, if you are more comfortable saying it in Farsi, please do. And I can also like help you translate. Or just mix the languages, I think. I think non-Farsi speakers are getting a bit used to it. So I'm sorry, but
It's for Farsi. I mean, this workshop is for Farsi speakers, so don't feel just feel totally free. I'm just here to like help, so don't worry.
I can go next if that's all right.
yeah.
I am open to, adjusting my idea depending on, the team, but my initial interests are kind of in two different areas. One is lighting. So this is something that I've been interested in before this workshop, but, using these origami techniques that we've learned to create some kind of like lamp or like cool aesthetically formed lighting structure for the home, I think would be cool. And then my second interest is with like awnings or like shade type of structures. So not necessarily function oriented, it's a shade structure, but how can you incorporate cool forms through origami within that to be almost like sculptural displays at outdoor events and exploring that type of avenue as well. I'm personally more interested in the physical prototyping and designing process, but I'm not opposed to learning about the digital components as well. And I can like laser cut or CNC wood or 3D print when I go to school throughout the week as well.
Awesome. Thanks for sharing. I think a lighting would be a really cool application. There are already some pretty famous like origami inspired like lamp shapes or these kind of things. It is really it's really interesting, and I think it works well with even the paper or similar material. And you can maybe add functions based on adaptivity to that. Some opening and closing, which would be really cool. And cool forms and sculptural displays also, because these forms are beautiful. Not to be too biased, but they're really beautiful. So. Okay, cool. So next.
Can I go next?
Yes.
Is it okay if I share my screen? I just stumbled upon a few examples that were interesting, if that's okay.
Yes, of course.
Yeah, so my interests, do you see my screen?
It says you're sharing. Oh, yes, we can see now.
Okay, so my interests are more in lines of self-assembly and looking at a larger aggregation of forms. So this was a few interesting patterns or forms that I saw that form like a larger structure by actuation. And the swarm robots that you showed us yesterday, it was really interesting to see how like a 2D form could form like a bunch of things and self-assemble perhaps. And this was a really interesting example that I've been looking at since I did my thesis research, where the same form can constantly change based on these actuators. But of course, in our case, it would be water. So this is something I'm looking at. I'm not sure how well it works, but it's just an initial thought. So that's why I was trying the cube to see if we can do like a bunch of cubes, but I'm not sure how well it would work. But yeah.
Cool. Yeah, really cool. I mean, I can also like, there are some examples of this like kind of aggregates of structures that like they each individually form and then they can also work together somehow to create an aggregated structures or like a surface that is made out of these patterns. Like more in the context of metamaterials, maybe that like the whole surface forms into something because each small part is changing shape in a specific way. So I think it's a really interesting idea.
Okay, can I also go next?
Yes.
So since yesterday when we were talking, we also had like three candidates of the projects that we can work on. The first one was wasn't any function or any structure, but rather a motion picture, which is composed of the typography of the words. That, for instance, we write down the word curl, and then you see that the curl curls as it gets the moisture. So the basic, the idea, and or whether it opens up or it closes, or it curls, or it curls. And so that was one thing, combining typography, which is one of our interests, with this idea of movement. Second one was lampshades, because it also has the open and close structure, but we were worried whether the heat of the lamp might affect also the opening and closing, or whether it would be safe to have the lamps near something that works, near something that the stimulus is the moisture. And the third one was a pavilion, which also when it rains, then it closes. When it's like dry, it opens up, and it opens up. And the basic structure was curved foldings, and that's the basic raw idea about what we were talking since yesterday.
Okay, all really cool ideas. Let's just start writing them down. But yeah, I love all of them. Combine it with typography would be really cool. You know, there are some examples of, for example, interactive books or stuff that like light up or sound up, but there are very few examples of shape-changing books. And this was one of the thoughts I had before starting this workshop. That would be cool that you get, for example, a coloring book that you only need to color it with like water paint, right? And then as you color it, and as you color different words, like curl, and then you see it curls up. I think that's really sweet. Lampshade, I think Ozin also talked about it. I think that's also really cool. So one thing that I was like try to explicitly say is that the model you make can be a model of something that will need to be produced with another material. So lampshade would be perfectly produced with this more like heat sensitive plastic laminates. You can maybe buy them. They're not too inaccessible, but maybe in 2 days that would be difficult. So you can make a mock-up of it with paper. You can maybe pre-moist the paper, and as it dries, to see, like, take a video of it opening, and kind of leave paper as placeholder material, but still show that this kind of interaction motion can happen. And a pavilion with curve folding would be awesome. Tiffany, do you want to say something?
Yeah, just I think these are all really great ideas. And I'm already starting to see a couple of themes with some of the groups already. And I guess just to like, Ali, are you specifically interested in curve folding, or because you mentioned curve folding for the pavilion, but like, or are you just interested in curve folding as like the base sort of mechanism for all the things that you mentioned?
Because of yesterday's lecture, I thought that the curve folding is much more doable in terms of prototypes, because when we introduce the straight lines, then we don't have like straight lines. We have like slightly bent river of papers. So that was like, I guess, the basic intention behind that. And apart from that, I like the curve fold. So probably both of these, but it doesn't have to be. I mean, if there's any solution to prototype that in a non-curve pattern, that would be also amazing.
Okay, cool. Yeah, just wondering. I mean, for instance, it was interesting to hear like Fatima, for example, was interested in combining the different types of like bending and folding. So yeah, it's just good to get an idea of what people are open to. Cool.
Can I go next?
Yes.
Okay. I really like to try something new, and at first I decided to try something in fashion actually. Well, I draw some sketch, and the main idea which I think about, which I thought about that, is to combine fabric layers with this with papers actually, and I'd really like to see how it will react with fabric layers when we add fabric layers to papers actually, and so I decided to try something in fashion categories. So I'd really like to test some design some necklace which expands. I don't know is it a good idea or not, but yeah.
Yeah, that's really cool. Definitely one of our other favorites on body wearables and fashion. I think this is also very interesting to try to combine these with fabric. I have not done that before, so you will need to do some tests to see if it works, but that's very nice. And it's also relevant to this whole concept of adaptation. Because human body has heat, has moisture, so something adaptive makes sense, makes a lot of sense.
Yeah, and I just to quickly add to that, I think you might want to also think about what properties the fabric has, because you know, some fabrics might actually be hygroscopic and also might expand. So when you do this experimentation with paper or fabric, you know, it's interesting. Just think about, you know, what properties are of the materials you're selecting.
Yeah, that's really cool. I think like maybe fabrics with cotton, like pamberi or katuni, they might be hygroscopic, so you might not even need paper. But yeah, we haven't tried that, so we will need to explore. Cool.
Can I go next?
Yeah.
I'm interested about wearable architecture too. And I did something before about wearable architecture.
Okay. So about adaptive architecture?
We use minimal surfaces for some stuff like hat or something else.
Okay. So either architecture or wearable, but about minimal surfaces and surfaces.
Yes.
Yeah, cool. I think a lot of people have similar interests in this.
Okay, can I be the next?
Yeah.
Okay, I will share my screen. Can you see that?
Yes.
Okay, yeah. So I have a couple of ideas. So the first one would be the curved folding furniture. So basically, there's a commercial product called this flex chair. So they just build the kind of developable surface and then finally manually fold into a chair shape. So I think with hygromorphic motion, actually we can do this automatically. And also there's a few other models we can try. So basically maybe this one is kind of like a sofa shape. So they activate the shape by using the strings, but as long as we have the hygromorphic stuff, we can also do it automatically. And also for some star shape, and this is kind of a warm shape. Yeah, and the second idea is about the reconfigurable objects, or it's also called these developable mechanisms. So basically, all the underlying shape of these three models are developable surface, which can be made by papers. So and on the developable surface, we can kind of cut small regions to form like a 3D linkage, and with maybe we just spray the water on it, it can move like a real linkage mechanism. And another idea is about the bistable structure. So for example, this is kind of this is a plant, and actually it can move into different phase. So either folding in horizontal direction or folding in the vertical direction. So actually, maybe something we can try is we can make kind of small structure with this bi-layer stuff, and maybe if it sucks sucks the water from one side, it goes to one shape, and if it sucks paper in the other side, it goes to another shape. Maybe it's a bistable hygromorphing shape. And the final one will be maybe some hygromorphic packaging. For example, if we have a tea bag and we just put in water and it changed the shape, maybe it looks fancy. For example, if we want to have maybe jasmine tea, maybe we can make maybe maybe separate tea bags. For example, the leaves would go down and the flowers maybe go up by the shape changing tea bag. Yeah, that's all I have.
I think it's only missing me.
Oh, wait. Give us 1 minute to reflect back on Rand's idea, because I think they're really cool. Yeah, so starting with this tea bag at the end, this is like one of those application scenarios that we have like direct water and interaction is cool. It's kind of like edible, people have it, people like to have new experiences with it. So I think this is really, really, really nice. The bistable structure is also pretty cool. One of the persons, Ozzy? No, not Ozzy. Sorry, one of the girls who is missing right now, she wrote to me before, and she tried to create a structure that when it's wet, it's like this kind of bending direction, and when it's dry, it's like this kind of bending direction. So she was trying that. She didn't make it yet, but I think something like that. When I watched the image of that plant, this plant, it is kind of doing that motion. So somehow, if you can get this kind of like different curvature in wet and dry, you can make those kind of bistable structures. Which is really cool. And care-folding furniture is also really cool. I mean, yeah. Oh, and those linkage mechanism, I have also seen that paper. I think that can be nicely combined, maybe with curve folding, because it kind of has like sharp hinges in those linkage mechanisms. So it's a combination of bending and some, yeah, I all are really interesting. So let's see how the interests are from the others. And yeah, it was Saba who was trying to make that double curvature. Okay, sorry, Marina, you can go ahead.
No problem. Saba is missing today. I actually honestly do not have a close idea. I thought about making something like a smaller scale architecture, like a pavilion or a canopy that changes shape with the weather, or maybe a facade that closes and open. But I'm also interested in product design in smaller scale objects such as furniture. So I really like also Azin's and Ali's idea of doing lamps, and also Rand's idea of doing chair. And I'm comfortable in modeling in Rhino and Grasshopper, and I also have a 3D printer, so if needed, I can print it here. But I do not have a wood filament, I only have PLA. Yeah, so that's
Great.
Cool. Would you say that you're more like interested in like the application side for from what you explained?
Yes.
Okay. Okay.
Yes.
Cool.
Okay, cool. So really interesting, really interesting ideas. I think I think some of you are more interested in developing architectural concept, which is pretty nice. And I think maybe this can be like one team of students, one or two architectural canopy or modular facade. I think a lighting element was one of the one of the things that many are interested. Maybe like self-assembly idea can be combined with either architecture or with the furniture idea. So, what do you guys think? What do you think, Tiffany?
I'm just trying to like highlight the ones, but I also don't want to force, anything. So maybe, I hope from this kind of sharing of everyone's ideas helped you already think about certain matches. So I think maybe we can take a short, I know we just had a break, but maybe we can just take a short like couple minutes so that I can like look a little bit and then you can also reach out, take the time to sort of reach out to some of the others if there's a natural inclination towards another like teammate. And what do you think, Yassi?
I think that's a good idea. So here you can use a chat function to chat people individually. You can just talk here with each other if you want. I can also make breakout rooms. But let's see. So I think I and Tiffany can look at our notes and you can just start talking to each other if you just want to work with some.
Yeah. Actually, that's a really good idea about the breakout rooms, because also I think it would be nice to have maybe for the students to have sort of a conversation without being like live streamed.
Oh yeah, actually I can stop the live stream. I think that is a good moment to do that because
okay, great. Let's just stop it so that we
should have some free discussion. Yeah. Okay, bye people on YouTube. I hope you enjoy our workshop. Okay.